All right. Hello, everyone. So I'm going to be kicking off day 2 for the OAIC workshop. So day 1, we were talking about, let's say, how to deploy the RIC and how to set up the ORAN system and how to get xApps deployed. But this time I want to go into how we develop xApps. So for this demonstration, it's going to be a lot of explaining like how some code works, and I'm going to be showing a lot of examples, but we're also going to be deploying an xApp as an example. We're using a slightly different system than we were before. So if you would like to follow along, you can, but it is also okay if you don't. In the sense that I will be going a bit faster through the deployment of the xApp steps since we've done it once already, although the steps that we're following are a little different. So you can see as we're going like how you feel about it, because we want to make sure that we have enough time to cover all the information. So with that, I'm going to just go first into the background and follow the website and follow this documentation. So this is the day 2, so you can find it on the OAIC website as previously. And I would just be mostly going through this as reference. So
yeah, if you could mute your own laptop, I think the other one is.
I just read. Yeah. Thank you. Okay. So oh, now I can hear. Okay, but anyway, was it coming? Yeah, I think it's like the speaker. Wait, how did I?
I'm gonna mute the speakers. That door's locked. I think I can.
Oh, okay.
They're off. I'm not able to mute them here.
Yeah. Oh yeah. Yeah, and I still saw it muted on here as well, so which is good. I didn't realize that as well, but we're good. Thank you. All right, so yeah, I'll just go into the background right now. So first off, the question, just to clarify, what is an xApp? So an xApp is an application that's deployed to the near real-time RAN intelligent controller, the near real-time RIC, and it's capable of communicating to the RAN. So note that there's also a non-real-time RIC, and we call the applications that are there RApps. RApps can run basically you use control loops between these applications. And for RApps, it's anything that takes longer than the second. And for xApps, it's between 10 milliseconds and 1 second. So an xApp can be developed in any programming language, but to be ORAN compliant, it needs to be able to communicate over the E2 interface. So in ORAN, the E2 is essentially the way that the RAN and the RIC communicate. And there are E2 nodes in this system. So an E2 node refers to a component of the RAN that can talk to the RIC, and usually that refers to the base station. But you could have E2 nodes as long as they comply with its standard. So for this demonstration, we're going to simplify the process of development such that we're using an E2-like interface is what we call it. So that enables us to focus on the functionality of the application. And what I mean is we're not going to go too hard or too specific on the details of how the E2 system works. So there's a lot of things about encoding and decoding ASN1 messages. They have subscription processes and things that are a little less stable when we're trying to prototype xApps. So from our end, we're going to use this E2-like interface, which just simplifies the connection a little. But yeah, so this is like the system that we would have, where we have this E2 node would be like the RAN, for example, and it uses this E2-like agent. So, or an E2 agent would be normal E2, and it would communicate to the xApp through an interface. For our case, when we're doing an E2-like xApp, we're doing a server client model. So essentially, we have a server that's based on SCTP or Stream Control Transfer Protocol, which is what E2 uses under the hood. But essentially, we have the base station communicating between the xApp, and they're able to exchange information in a specific way. So then the xApp can run some code or whatever we might want to, and then we can send control decisions back to the RAN through xApps. So to understand how an xApp works, and then fundamentally, at least within ORAN SC, we need to talk about how the ORAN network is implemented, especially for the RIC. So the RIC can control the RAN dynamically, but the RIC actually consists of a Kubernetes cluster, which you would have seen from installing before, and it hosts several components which contain services and pods. So if I take a look at all of the pods that we did when we were deploying ORAN software communities RIC, we can see that we have a lot of different deployments which contain different services in the RIC. But we have these deployments, and so there's different pods that contain the resources for some service to operate, which usually refers to Docker containers. So I'll just read it straight off. So an application such as an xApp is executed in the RIC using a deployment, which consists of the instructions and components that are needed to run the application. But inside this deployment, there are pods, and they contain different microservices, which are small Docker containers running different software and make up the application. And the containers that we use are created using an image, a Docker image that we prepare beforehand, which consists of the environment and everything needed for that application to start at that given moment. So if we, yes?
Can you tell us in layman's terms, what is a pod?
A pod is essentially a way to, or it's a group of, So, I mean, it's a group of containers, but a containers refers to the like if we think of virtual machines, let's say, we would have a system that we're running, like we're emulating in a way, or not necessarily emulating, but we're running a system inside of our system in a virtual machine. But with a virtual machine, what we're doing is we're taking the CPU and the RAM and the different, like the network, the Ethernet controller, the whole operating system, all of that we're replicating in software. And the difference is that when we're using Docker actually will use some resources from your own system, and it's a lot more minimal. It's a smaller minimal state of what a virtual machine would offer. So essentially, you can, if let's say when we use Docker containers, we're often running something in Linux, and we're installing some packages. And it essentially what we end up with in Docker is that we are storing like the state of the current. We're storing the state of some Linux machine that we're running.
Yeah,
but it's
yeah.
Yeah.
So here we see 3 blue pods, right?
Yeah.
Each blue pod could have one or more containers.
Yes.
So one option would be I have one pod and many Docker containers, or I could have many pods and one Docker container. So what is the difference? How do I separate them?
Yeah.
Or it is just the framework and you can choose any.
Yeah, and I'm not going to say that I'm an expert in how you would deploy this in IT, but Pratik, if you have a better answer.
So basically, pod gives you an environment to house your containers. So what I mean by that is, let's say you have an application, right? Yesterday we deployed the E2 interface. We pulled some containers and we deployed the E2 interface in that thing, right? But what we also did was we hosted a web server. We called that Nginx. Now that Nginx can be a separate entity. It does not have to be dependent on the E2 interface and the near real time, right? But the E2 interface and the xApps use that Nginx web server, right? So what you can do is you can take these two independent applications, you can make them containers, and then house them in a pod.
One pod will contain both.
One pod you can combine multiple containers.
Okay.
One pod can have just one container. That's the most simplistic approach. So let's say you have a Docker container, you can just deploy it as a pod. Why would you want to do that? Because it helps you in scaling up. Let's say you want the same instance of the Docker image, multiply hundreds and thousands. With one command, you can just say, okay, Kubernetes, give me 100 instances of this particular container.
So the pods would make it easy.
Yes.
To quick.
Yeah. And then if there is a fault, right? Let's say there's a fault in some container, it's not running. Kubernetes automatically reports it to you. Let's say you are the system administrator. It will automatically report to you and say, okay, this pod 51 is failed. So look into it, or it will restart on its own. You can automate that process. There are many methods that you can use. So that is the concept. So, or you can have multiple containers within a single pod, depending on how big your application is or how small your application is. Makes it easier to customize and control.
Yeah, and it like depends on how the services are meant, or like the microservices, like the containers. If they're only operating with each other within the pod, then it might make more sense to do that. But if you have a web server that's talking to multiple xApps, you might either want that in a separate pod or its own deployment, like to have the web server in one deployment. And most of these pods that are here are often, or like for example, our xApps are separate deployments entirely. And so they could, if we had a web server in this cluster, then we'd probably also have that as a separate deployment.
So here they have made it very simple. So you see one. Yeah, one by one. Right? That means one container.
One pod, one.
Yeah. So it is showing that one of them, Prometheus, for example, is showing 2 out of 2. Right?
2 out of 2.
So it means there are 2 containers and both of them are running. If it shows 1 out of 2, one of them has failed. So that way you can keep track of it.
Okay.
Yeah. So, and it's not like, for our purposes, we're going to simplify this a lot. So in our case, like for the xApp, all you really need to understand is that we're using a single Kubernetes deployment, and it has a single pod, and it has a single Docker container inside. So we're not doing anything complicated, running multiple services, but that's just a good example of what you can actually build up. So, and thank you, Pratik, because that was pretty well said, because that kind of explains why we use Kubernetes too in the first place. We have to, like, when you're trying to scale things up in the cloud, for example, or if we're trying to, when we need more than one instance, or we need to be able to spawn up things quickly, like it makes sense to use Docker and Kubernetes for that. So now I'm going to go into the workflow of like how we actually deploy an xApp, and I'm just going to go through it briefly because we're going to do it directly in a second. I just want to overview it, because we're going to look at the different components in the ORAN SC RIC that are used in the steps to deploy an xApp. So the first step is having a config file, which is it's basically a JSON file containing the configuration, Docker image name, some ports, and supported messages that are for that specific xApp. And we take this information and we submit it to the xApp onboarder. So the xApp onboarder is a service in the near real-time RIC which accepts the config files, and we convert them into charts. So it'll store some information as charts in the onboarder. And a chart is basically just contains instructions on how to deploy the xApp, eventually deployed in Kubernetes. So then we interface with this app manager. And the app manager is another component where we can tell it when to deploy or undeploy an xApp. So based on any charts that are already in the RIC, it can find the name of whatever xApp that you specify, and you can ask it to start it or stop it. And then when it starts it, then it'll go into the Kubernetes cluster as a deployment, and we'll see it running like this. So yeah, that's the main deployment workflow. Yes.
So the xApp that we created yesterday, does this decide it?
So
It's going to start from scratch.
it can live beside it, and it won't affect it in this case. Since I'm doing like a slightly different approach, we can use the same RIC, but it's going to connect in a different way. So so if you have the xApp that's already running, it shouldn't interfere with it. So, but yeah, for following along, we're going to start with some setup. We have a different SRS-RAN version that we're using. So during our steps, like while we're talking, I'm going to suggest that we compile SRS-RAN. And so basically we'll be following these steps to build the new SRS-RAN. And while it's running, we'll just continue on with the other steps, since it'll take some time.
Okay, are you guys ready to follow or you need some time? Does anyone need some time? You need some time? Okay, we'll give you 5 minutes. So please
Okay,
give me
yes.
5 minutes. Thank you. Because once Nathan goes, we will move faster.
Warning.
5G or maybe 6G. Okay, so I want to make sure that you are on that train.
Yeah, thank you, Doctor. Yeah.
So Nathan, right now they should go to the OAIC website. Is that correct?
They should
For
be.
the where should they go?
Oh, if they want to, yeah, if they're getting on this website, it's under the day 2 developing a custom xApp in Python near the bottom of the OAIC website. Yeah, you might have to do Control F5 or something to force refresh it, or Control R. Actually, it probably would. You probably don't have to, but but yeah, definitely refresh. Yes. Yeah, you're good. Yeah.
Do we have Oliver in this room? Oliver? Oh, who you are Oliver? Oh, you are Oliver. Okay. Yeah, I just wanted to make sure.
Who's in the
Looks like
Zoom?
there is
Yeah.
no real remote Zoom person up to this. Okay. Or whoever is there is here. So Nathan, everybody.
Good.
So
Yeah.
far. If some Zoom person comes in, I will let you know.
Okay, thank you. All right, well, I'll leave this up for a bit so we make sure that we're. Is everyone okay? All right, so I think we're okay. Yeah. So, awesome. So first thing is that we're going to go back to the OAIC folder. Even though the step doesn't show it here, for most of these steps, we assume that we're in the OAIC folder. So I'm going to go there on my system. And then basically we just run these steps. It's similar to what we did to install SRSRAN in the past. It's just that we're going to change some of the flags which are here. So if you use the one that comes with OAIC from the previous steps, make sure that it's SRSRAN E2 and not SRS LTE E2, because the LTE was the modified version that was being used for yesterday's xApp. So in the steps here, make sure that you first CD to SRSRAN E2, which is the one that comes by default. So then you should be able to follow the same steps that you did before. I think I already have a build folder, so I'll just remove it so that we're on the same page. So you make the build directory, and then we have a variable just so that we can use it later for our cmake command. So I'm going into the build folder, and I'm going to copy the cmake command. And something like that should show up. And then as long as it says those, then you're good. But yeah, if you were able to build the SRS LTE before, you should be able to not have any issues getting there. Yeah. Yeah.
Does anyone else have a question? We can have volunteers help you. Anyone?
Okay. So I'm going to run make jn proc, and I'm gonna wait for it to finish. Mine will probably be a bit faster. So while that's going on, basically at your own time, like I will follow these in a second. So when you guys finish this make command, then you just have to run sudo make install and the next command, or just the following commands after. And then once SRS run's built, then we'll continue through the rest of it. So since I'm waiting for it to build, I'm gonna skip a little. So I think, yeah, I'm gonna wait for this to go because I'm assuming that y'all are gonna take a little more time. So I'm going to focus on the development section. So at this point, we're going to talk about what the xApp looks like in terms of code, and we're going to look at how can we do different things through xApps. So first, we're going to look at this rick app ml e2 like directory. So I'm going to go in a different tab, and so we're going to look for the OAIC. In the OAIC folder, there's a rick app ml e2 like directory. So I just want to show you there's different files here, and this is the files that we need to create the xApp. So we use a Python file called app.py, which stores the main code of our xApp. And in this file, we set up a connection for SCTP, and we run a constant loop to receive connections from any base stations. And then we receive data from them and send control messages to change the RAN's behavior. So for our case, we use E2 like SRS RAN to receive IQ data, uplink IQ data directly from SRS RAN. And we can use that to generate spectrogram images and analyze information about channel using the xApp. So when using the E2-like interface, well, yeah, this is what I said. The xApp is the server, and then base station node B is a client. So we're going to take a little look at the code. So this is the code that's relevant here is that we're essentially starting a server and we're accepting connections. So at first we have some code here which finds the IP address and the port that we need, and we start an SCTP server using these lines of code, and we start listening to any available connections that we're getting. Then we have this entry. After that, we have an entry point where we are initializing the E2 first, and then we enter an endless loop. So in the endless loop, we're accepting any connections that we're seeing, and then we log that we've made that connection. So from there, we start receiving, or first we send a request. So the way that the E2 interface usually works is that the base state, the xApp will communicate with the base station through indication and control messages. So indication message is when we're sending information from the RIC to the RAN. So if we're receiving any data, and then the control messages are when we're forwarding any commands from the RIC or the xApp to the RAN. So when we do an indication message, there's a request that we have to send first. So we send an indication request from the xApp to the base station asking it for data. And what we do in this code is we just send a request like this. It doesn't really, in our case, the way that we wrote the code doesn't actually matter what you send here. But yeah, in real E2, there's a specific way to send an indication request. So we send a request first to get data, and then we receive chunks of data in bytes from the node B. But if we send too much data at once, it actually will freeze the connection up for SCTP. So we send less data. We send about 16 kilobytes of data at a time. So eventually we receive enough IQ data to make 10, or we receive 10 milliseconds worth of IQ data. That's what we're doing in this program. And we use a spectrogram size. Oh, well, it's not in this code here, but until we reach the full size of the data, we just keep receiving data. So once we have a full buffer of the IQ data, we can process it and then run some prediction. So if we're using machine learning in this case, we would have some model that can process either the IQ data, or we can process some image data that we generate, or any information that we extrapolate from that. So if we look at the code for this run prediction here, we have two components. So first, we actually convert the IQ data into spectrogram image. So we use that as input for machine learning. So the code is not shown here, but essentially it uses matplotlib, and it takes the data and generates a spectrogram as some pixels, some RGB pixels that we can process into some machine learning model. So then we make a prediction. So we'll have some like predict function, and we'll do some model predict or whatever, and decide which classifier it belongs to. So in our case, what the xApp that we want to design is something that can identify any interference that's present in the system. So if we detect interference, then we can send some command that will improve the network's performance. But if we get like just LTE or 5G, then, and that's the highest thing, then we probably don't have interference. So we essentially make some prediction using the model. In our case, for this test xApp that we're doing, we don't actually have a real model. We're just going to send some random information, detecting LTE or 5G every 8 seconds, and then detecting interference every 8 seconds. And the reason is so that we can show the control features that we have in the xApp, even though we can't simulate interference directly in this demonstration. So if we go back here, we've like made a prediction. So if there's interference, then we can send some commands to improve the network. In our case, we're actually changing the modulation and coding scheme. So there's a dynamic algorithm that is built into SRS-RAN that will change the MCS according to the CQI and other channel conditions. But we have it off by default. So we only turn this on when there's interference. And through that, we will see that there will be a decrease in the error rate. So when we detect interference, we send a command to enable the adaptive MCS, and then otherwise we turn it off and we have a fixed value. So yes.
So, but I didn't think, so here you're getting back IQ, right? So I didn't think the E connection comes all the way down to all the bottom of the DU.
Yeah, so what you would have to do, and it depends, because for our case with SRS-RAN, we can make file layer decisions. So since the DU and the CU, if the DU and CU are co-located, for example, then so the IQ data is collected from the RAN itself, and then but since the DU, CU, RU, like they're co-located, and I mean, depending on which split you're using for 5G, then technically the file layer you could have some of the file layer interact with the RIC, but I can't remember which functional split it's called, but there is a way, like in some cases you can actually have some of the file layer directly interface with the RIC in a way. But yeah, so
cost between, then you can access samples directly to the CPU. And for the CPU, you can access the free tool. So you can collect the samples with other simulated non-standard for ORAN, but it's and obviously xApp will still be not near real time.
Yeah.
Not real time, right? So it will be kind of delayed or faster.
Yeah, we'll need to continuously collect a buffer of data, and then once that buffer is filled up, then we can make a prediction. So IQ data is just one type of thing that you can send, and normally it's not going to be, for example, it's not ORAN compliant. So we also look into using KPMs or like metrics about the network's performance. So let's say simply just a bit rate or error rate, CQI, things like that. We can just send that type of information. But we find that, but you'll find that that information is hard to extrapolate what is going on in the network. And for example, if we have a spectrogram image, so like, for example, this is what it would look like from the LTE data. If we had some interference here, we'd be able, if we had some detection model that we could pinpoint the exact location of where an interferer would be in the system. So that's why spectrogram data can be helpful, but there is a higher overhead that comes with that. So this is the way this is the main components of the xApp that we're about to build. But I also do want to touch onto other parts of xApp development that even though we're not showing that we're not directly showing in the code that we're about to run, I also want to talk about how we can, expand this knowledge to integrate xApps with your own machine learning models, for example, or to like receive KPMs or other data that we like. So there's a section that we'll talk about, which is integrating machine learning into xApps. So we're going to think of a scenario where we have some machine learning model that we like to implement, and we are collecting KPM data. So we would, in this case, I think we are only looking at bit rate and error rate. So just as a small example. So if we look at neural networks, we can view in terms of our code, if we know whether we know how the neural network works or not, we can think of it as just like a black box. It takes some input vector and it gives us an output vector as a result. And our goal is to convert the inputs to the format that our model takes, and then to be able to interpret that output from the model. So let's say we have some like deep neural network model that can classify that state of the network based on bit rate and error rate. And if we assume those are the only KPMs, there are 2 values per time point. But it's probably a good idea to look at multiple time points at once in the model so that we see, like, for example, if we're looking at interference, we would know that there's interference because the signals, the quality, like the error rate increases and the bit rate decreases. So you would need to know a little bit of past and present information to do that, or like multiple points in time to be able to define that. Yes. So the actual oh yeah, so I'll have like a no interference and an interference, let's say, maybe. But it could be 1 because if you have like the probability that there is interference. But I just have it as 2 classifiers. So like let's say like LTE signal or interference signal. But yeah, it could be 1 output as well. Like, because all we need to do is really look at like the confidence of how sure we are that there is interference. So huh? Oh yeah. Yeah, we're just analyzing what what they are. So instead of trying to recreate that is an interesting thing. I never thought about that, but I think that's cool. So what we're essentially doing though is for the system we would have something in SRS RAN that sends us some KPM data, and we can save the time points as we get them from the RAN. and then just keep them in some buffer or array that that eventually fills up. And once we have enough time points to shove into our machine learning model, then we can make a prediction. So here I have like a 2 by 10 KPM. So let's just say that it's an array of 20 values. And so once we have enough data, so let's say greater than 10 time points, if a time point consists of the bit rate and the error rate, then we can handle how many data points that the model can take. So we said 10. And then we can just restart the array and start receiving new data after we make our prediction. So an SRS ran though, like this is the xApp code just for reference. But also in SRS ran, we need to be able to change how it behaves. Like how do we decide what data we want SRS ran to send to us in the xApp? So in SRS ran, we're using the 4G code base for this, but we pinpointed the areas where we can decide what information we'd like to send. So for example, if we have some IQ data, which we were talking about before, we have to receive it from the phi layer and pass it over to this agent.cc. So it basically just uses a send SCTP data. So as long as we have some buffer of data, we can just loop through and send all that data over. And that's what we have in the SRS ran E2 that we're using right now. But there's also this for KPMs. We have some sample code that's in the documentation, but it's not written in SRS ran for you yet. But the idea is that we can modify this agent handle message code to handle the E2 or E2-like messages, whatever we receive from the SCTP. We can handle it in what way that we'd like to for our interface. So if I go back to here, because it's more simplified at least, we have this like metrics. SRS ran actually exposes a few ways to just collect the overall metrics for the node B and also for the UEs. And they also split it in terms of like the phi layer, MAC layer, RC, and other things. So we actually can sum up since these metrics are per UE, we can sum up the uplink rate and the block error rate for all of the users at once. And what this code does is it loops through each of the UEs for the RRC, or well, not necessarily RRC, but it could be MAC or whatever. But we're looping through the amount of UEs that we have, and we add up the bytes of the uplink rate, and then also the error rate that we're getting as well. So that's what that code will do. And we can essentially just what this code is doing is just sending that information in bytes over the E2 like interface. And then if we look back at that Python code, we really just have to receive those bytes. So we know if there's uplink rate and block error rate, we know that it's 8 bytes, or there's 4 bytes each because those are floats. So just knowing that there's 4 bytes each, we receive 8 bytes, and then we can treat that as a single data point. Then we can have some code that will convert every 4 bytes to a float, essentially. So this handle KPMs function's goal is to take whatever the 10 data points that we have, so 20 KPMs total, and make some prediction off of them. So we have this KPM floats array, which converts the bytes into floats again, or into decimal values. And then we have some prediction, which, for example, like if we're using Keras, we can use like model predict.sample. For PyTorch or PyTorch Lightning, I think it should be just model sample. So you can take that input and you get a prediction out with some output. So if we think of the output as structured like this confidence value for signal without interference and with interference, just in this case, we can decide like which classifier we think has the highest value. So we can use, for example, NP argmax will take like some value like this and find which classifier has the highest number or highest confidence value, and then what is the confidence value. So then we can store those information and return it as a system, or return it as like a tuple. So we just convert the classes, like it says max index here. So let's say that this is without interference, this is with interference. If 0.5 is the one with interference, then it will give me a result of 1 because this is the 0, 1 index in the array. So this is the 1. And then it would look it up in this table, in this dictionary, and we would get signal with interference. So that's the result we would get from the code. So essentially, from here, we can decide how we'd like to act on such a system. So we could set a minimum confidence value. So we can look at this and decide, are we sure enough that there's interference that we actually want to take action? Or do we want to accept the highest prediction every time? Like, is that acceptable? So then once we have a prediction, we can use that to send commands back, as we saw previously in the xApp code. So that's the main parts of the xApp development that I wanted to go over. Yes.
So this is near real time. We're running C code on the SRS run side. We're running Python code here. Is it fast enough? What are the time constraints?
Yeah. So
Are we, in other words, are we computing something and then telling it to just bit error rate after that sample is already long gone?
Yeah. So okay, this is a good question. So it depends on how fast your loop is running in general, because we might be receiving 10 milliseconds of KPM data or we might be receiving 10 milliseconds of IQ data, but there might be some time like interim time in between where we're not receiving anything, and then we ask it to receive 10 milliseconds again. So yeah, so there's you'll have that point in time where you're waiting on that xApp to do the decision. In actual E2 interface, they specify, you could specify a timeout, or basically how long is that control supposed to run. So between 10 milliseconds to a second, knowing how fast your system is expected to run, or how long it needs to run, because maybe if it doesn't respond within that time, you just tell it that it failed, and then it'll try again next time. So.
But I think what covered it yesterday, the channel state changes a lot faster than milliseconds, depending on
Yes.
moving or not. So by the time you get this question, by the time you get information about the state of the channel, and you say adjust, so that's all.
Yeah.
I think but looking, trying to get that data a little bit faster, so this way you can turn around and have a.
Yes.
It depends on application. So if he wants to do MCS, obviously you need to be real time.
Yeah.
But if he wants to do something like spectrum sharing, where the LTE that is here is a shared band, or radar, for example, the primary user, then the standards say you have time, you have like a second of time to vacate the spectrum.
Exactly.
So it depends on the application. Might work the way he's doing it. And if not, it's a starting point to go to the real time.
You said from the axis, you said a minute, 1 minute, or few minutes?
Oh, for the radar?
Right?
Yeah. For the CBRS band,
Yes,
it has to it can take up to 1 minute to respond.
Yeah,
So.
it depends on the application.
No, I think you're right. If you have the radar that's known, you want to share spectrum, it's one thing, but you're trying to detect the channel quality as you're moving, that's the thing.
Yeah, that's true.
That needs to be done.
Because if you need like, for example, for our MCS thing, or when we're changing MCS, all we're doing is enabling the system in the DU to actually, in CUDU to actually pull that off. And because, yeah, for us, we can't like give it an MCS number in real time like that, or tell it, yeah. Thank you. Yeah, but those are great points, because when we're doing development, we need to decide if, like, yeah, what fine grain like time we need to operate in. So And I think Edric will also be interesting to talk about later because that is where we get into those like under 10 milliseconds of time. So I would be more. I haven't followed in terms of like we did it, but like vaguely, I would say. So like I didn't test, let's say, how big the model is and also the runtime performance, but I would say that well, yeah, like we did, for example, we took for the radar detection model, that was an object detection model and that took a lot of time. The entire loop ran in 866 milliseconds, let's say. And like, let's say 600 milliseconds of that time was just a model prediction. If we were doing just KPMs or something, or with a small deep neural network model or something, that will be within like single digit milliseconds probably, or something like some short time. So it would have been a lot less significant in the runtime. Yeah, that's the thing, is it gets lower. We got with the 20, or we did a test with 5 kpms and 20 data, so like 100 values, and our accuracy was like 80%. So that is but and then on the other hand, if we use spectrograms, we got close to 100%. So you could there's probably a good middle ground where it is for the prediction, whether it's collecting more KPMs or whether you just have a model that like having a better system in general. But yeah, so there's a trade-off, but I haven't followed, like, I haven't tried scaling a model on like one system and seeing like what is the sweet spot for that yet. You mean to the RIC, for example? Like if you said that there is interference or not, and then you were wrong. Yeah, so there could be consequences in theory, right? But it would depend. You would want to, like, in a real robust system, you'd probably want to have a way that, like, you want to know how much you can trust a model, or maybe you want to wait for one more prediction before you make a decision or something like that, where, because you know that you have to imagine that there'll be some false positives or false negatives that you need to account for in the system. If your system is changing really quickly and it makes a bad decision like once really quickly, it might not matter like in the long run, or it could matter if it's really critical that you get it right every time. So it's important there's definitely a trade-off in thinking about how making sure that the system is stable and gives you the right results versus how fast it operates. Yeah. So, but yeah, so this is I'm trying to see if there's any other information I'd like to show. But yeah.
So please keep in mind that we have these RIGs, right? Non-real time and real time. They actually cannot directly change anything. What they are doing, they are providing guidance to the protocol stack. For example, if you look at the DU, ODU, right, Orange Distributed Unit, that has the 3GPP defined GNB DU function. And one of the layers, let's say MAC protocol, medium access control, inside that we have a proprietary scheduling algorithm. So if I'm a vendor, I'm Ericsson, I have my own sophisticated algorithm. If you are Nokia, you have your own proprietary scheduling algorithm. So this kind of xApp or RIG, right? It provides guidance to that scheduling function, right? So we guide. So he provides the policy that, hey, do this, and then at appropriate time, if the vendor allows such control, right, then they will implement the policy. Okay. So we cannot really change anything instantaneously. Okay, we can only provide the guidance.
So I guess the managers so you were talking about like the schedulers, they have to essentially actually allow that. So you can
Correct.
send a policy, but they can choose to reject it.
Correct, correct. So the only thing Nathan can do, or any of us can do, is provide that guidance,
Just a little
right?
influence,
Yeah, and then it is up to that algorithm or the vendor's implementation to support each other.
Yeah. So in the way we think about we use this to make more informed decisions about like the nature of, if the xApp is able to look beyond maybe the one CUD, it can actually pull information from multiple cell towers, base stations, and give you a better, give you some more information that would help you in that prediction or whatever scheduling algorithm maybe, then that's where the strength of the xApp lies in. So, okay, I'm reasonably good on time. So I'm going to take a second to go back to the SRS ran steps that we were going before, because I'm assuming everyone who's following along, is there anyone who hasn't finished running the make command? I think we're okay.
Does anyone need help? We have volunteers to help you get back on track. Okay, looks like.
I think we're good there. So I'm going to just follow these steps again. So sudo make install will install our version of SRS, the latest or the current version of OAIC that we would like in our system. So I'm not in the right space because I was trying to demonstrate, but you would probably be here in this OAIC SRS run E2 build. So you can, if you run sudo make install, it should overwrite the SRS LTE that was installed previously. So I will just do that right now. And we get all of that, it'll show up. So then we run this next command. I'm not gonna actually run it because it'll overwrite my config, but you'll run this and it'll ask if you want to force install everything, and you hit enter, and it should overwrite the config files. Or install them in the right place, because they actually it won't use it installs it in a different place from the SRS LTE from yesterday. So once you've done that, you can just do the cd ... here and just go back to the OAIC folder. Then there's also an additional little step here if you want to use a text editor. What we would like to confirm is that if we look at this config, hopefully your config should also be in the same location. If you ran sudo make install and you did this, then you should be able to type in this root config srsran, the enode b config, and you'll get something that looks like this. If we go down, there's some arguments for the RF configuration, this area, and we want to make sure that this is uncommented out. In some cases, it might not be uncommented out, so it might just look like this, for example. So we need to just remove the hashtags from the beginning. And once we've done that, then we can save. So this is enabling 0MQ, because I think in yesterday it was built into the command, but I didn't build it into the next steps. So you have to just make sure that it's 0MQ is on for the configuration, because otherwise it might try to find a USRP or some hardware connected, or it'll just complain and tell you that you have to specify it. So if you have that, then you can just save it. It'll ask you if you're using Nano, and I don't know whatever text editor you like to use, but just for reference, if you're using Nano like me, Control X is how you exit, and then it'll ask you to save. You hit Y for yes, and then you hit enter to save, to confirm the save. I'm going not to save it. But we also have to do the same thing for the user. So it should show up. There is also an RF configuration in the UE-conf file. And that also should be uncommented like this. So where the ZMQ is the device name and device args are shown here. So I will make sure that is anyone stuck on that, or I'll just give it a minute to make sure. Okay. I think I will, yeah. Unless anyone is stuck, I will continue. So so the next step is we're going to actually create a temporary file system. So in this modified version of SRSRAN, instead of changing the variables in the threads, because SRSRAN operates on a lot of different threads, so having thread safe communication is a bit difficult. So the simple implementation that we had was that we were actually just writing to files to communicate information from the find to MAC layer over to the RIC. So we use this to change the MCS and to collect the IQ data. So, however, writing to the hard drive is relatively slow. It causes a slowdown, so it's not. I wouldn't recommend it, but there is a way to improve the nature of the system, and that's by actually storing the files in RAM instead of the hard drive. So we're going to follow these commands, which essentially just create. It will give me an error doing this because it exists, but essentially we're mounting a temporary file system in our virtual machine or wherever it is. I'll make sure I might have just deleted stuff. Let's see. Yeah, I did. So I'll follow the steps here. So we use sudo mount to create a file system in memory that's 64 megabytes in size. And we're going to touch, which basically just means creating these empty files. And then we use this sudo chmod rr. So it just means that these files will actually can be read and written when we're using them in SRSRAN. So those steps shouldn't take any time, but I'll just make sure. For reference, we have this agent command bin. It stores the e2like command that we've received from the xApp. And then we have a temporary IQ data buffer that SRSRAN is writing to, but when it's full, we rename it to IQ data last full.bin. So once this file system is set up, then we can just continue on to actually deploying it, getting closer to deploying the xApp, because I went over to development. So is there any questions before I continue?
Yeah, just open. So does this change if you're using G-Node B as opposed to?
So yeah, I would. Well.
Just let me know that. I don't want to.
Yeah. Okay. But for this case, we're running LTE, and it'll be on eNode B and everything. It's because the code will be a little different. SRSRAN behaves differently. For deployment, so we're going to talk about. We did run and talk about this before, I think a little. But we're first talking about the Docker image. So what I will suggest is that,
Real quick,
yes.
maybe a follow-up question. The E2 interface we're using is standardized, right?
Yeah, but for this demonstration we're using the non-standardized version.
But how standardized are the commands you send? For example, the command to request IQ data, command to adjust the modulation. Is that all standardized and would work on any program client, or is I don't know how deep.
So yeah, so the answer is no. For that, essentially, what we have, the way that E2 works is that if we want to implement some functionality in it, we have to create what's called a service model, and the service model is essentially just the types of messages we can send and receive. And as a result, that means that we have in the E2, for example, there's that There's the secure slicing xApp, there, which NextRAN is a slicing xApp that I believe is similar. NextRAN has a service model that works with SRS-RAN for slicing. So SRS-RAN supports that for the E2 interface. There's also KPIMon, which is an xApp for monitoring KPIs, which is in the ORAN specifications. So in the ORAN specifications, they do specify a way, this is how you're supposed to collect all these metrics. So this is how you should implement that in your RAN. But for any other functionality, we have to follow, or we have to come up with our own service model. And it could be like, if the model gets popular enough, it could be adopted into that, that standard. But in our case, generally, if while we're doing new things, it's expected that we'll have to implement both sides ourselves, the RIC and the RAN implementation. So with the service model, like, even though there's a structured format for it, the contents of the structured format, which is what actually matters for communication, that's not built in to everything. Yeah. So let me check something real quick on the step, so I don't. Okay. So I'm going to invite you all to also probably look at this, but you don't have to. Essentially, we should look into the ML folder for this xApp. So I would say cd into RICApp ML E2 like from the OAIC folder, which will give us all the files. We should see like the app.py Docker file and these other components. So the first thing that we want to look at is this Docker file. So I'm just going to open up so that you can see it. It's also right here. We have these different steps, and the Docker file contains all of these commands, or not just commands, but these instructions on how we're going to prepare our environment for whatever application that we're running inside of that. So the first thing that we do here is this Docker, this mini conda thing from Continuum.io mini conda. Essentially, we're loading an Ubuntu, not virtual machine, but an Ubuntu environment that is pre-configured with Python installed using mini conda. So this is the image that we're using as a base. So all that stuff is already installed, and from this point, we're in a current memory state where Ubuntu is ready to run another command. So in the next command that we run is apt-get update, and then we install all the libraries that we need for our xApp specifically. So we're just running Linux commands to make sure everything's installed. Then we copy all the files that are next to the Docker file, and we put it in some folders, so temp.ml. And then we change the working directory. So we make it so that all of our future commands will be running in temp.ml inside the inside of our Docker environment. So that's what workdir temp.ml is. Then we have requirements.txt. So this is just the Python requirements for the software that we're using. So it'll read that requirements.txt and then install everything that we need. And then finally, we're setting our xApp to run immediately when deployed. So this command, python free app.py, essentially we're just running the Python code, and that's the thing that will immediately run when we spawn up this Docker container or the Docker image. So just to show, we also have the requirements txt. It just has like matplotlib numpy, so loading images, being able to plot spectrograms, and then we have py-sttp, which allows us to connect through the STTP interface. So then once we have the Docker file, assuming that you have the system and the RIC and everything previously set before, we build this Docker image and we're submitting it to the xApp registry. So it should be similar to what we ran in the past, but there's the sudo docker build command here. and it will build and update it'll build the Docker file into an image and store it as xApp version 1.0.0. So if I run this, mine takes a little less time because I've already, when you run it before, it like caches the previous steps. So unless you change something in the previous steps, it'll be able to use the same states of memory that it was in previously. So then you'll have a built Docker image, and it'll be stored in the xApp registry. And we have this xApp registry because this address is somewhere that is actually accessible to the RIC and the cluster. So any of the services that need to deploy xApps, and for example, Kubernetes, will need to be able to download the Docker images to run the xApps. So that's why we store it in this location. And we spawned previously before we had spawned this with some commands, some Docker commands. So this registry is also running inside of Docker. So then I can continue to talking about the config. So there's a config file in the init, it's called in the init folder. There's a config.json file. So in here, we can see that there's some information about the Docker image location. So here we have the name and the version. We have the network details. So for example, what ports are we accessing this xApp through? And what types of messages in the E2 interface are we going to send for the specific xApp? Because since we can specify what types of messages we're sending, we will know that, let's say if this xApp was compromised, that it won't be able to do additional things that it wasn't allowed to do in the first place, or at least within the specification. So, for example, if we only want this xApp to send data or to send information, we want the xApp to only receive information from the RAN but not send information back, we can turn off control messages in this through the RX and TX messages. So we have, these are the main ports that we commonly see is this RMR. It's a RIC message router, and it's how we send information through the E2 and the A1 interfaces normally. But we're using a replacement E2-like interface, so we're going to be bypassing these and creating our own connection. But that is what's in this config file.
Where's this located? This file?
This is in the xApp E2-like in init.config.json. Yes.
Real quick, my requirements.txt doesn't have this. I just have.
Oh, really?
And I just did a git.
And you just did a git pull? Okay. Yeah. Let me make sure, because we might have to add it.
Anyone else check me on that?
Yeah, that might be good. Yeah. Let me also see. Yours, okay.
I just did a git pull.
Let me also double check. I see it in the repo, but it might be a.
What folder? Maybe he has a different folder.
Which one? This is the xApp ML folder. The PySCTP in requirements.txt, this line right here. I think. Yeah, I don't know either. It looks like it's there now, but I think it used to not be there. I added a fix, but it was about 6 months ago when I added the fix. So. Oh, because I don't have a new line on the end of the. Yeah, so it's like.
Oh my goodness.
Yeah, I just realized it when I did cabbage. Yeah. I forgot to add a new line to the end of the text file, so it shows up in the middle of the.
Oh, I see it, and I just didn't notice it.
Yeah.
My mistake.
Probably my mistake too. Yeah. Yeah. I need to remember to do that. Yeah, so that's the config file just to show you, and the requirements.txt. Those are just the different, this is all we need to like set up this application's environment. So for the next steps, we're actually going to upload our config file to the web server. So we've done, since assuming yesterday that you ran the steps, you should not have to run these again. This entire step 4, you should not have to run again. If you didn't do it before, then you would need to run steps 4, but you can just run them as is. Like you just install nginx, you make the directories, you edit this file and copy paste those in there, and then just run that command, and you're set for step 4. But I'm not going to wait on that because I assume that most people were following that yesterday.
Sorry, for the step 2, do we create our own config.json file?
No, you were going to use the init config.json. Sorry, in the init folder there should be one right here. So we would just use that one. Then let me see if, so step 3 says, yeah, okay, I'm just confirm. So step 3, we are just going to take our IP address, finding the local IP address. It probably is the first one that you see when you run this command. And we're going to save it as an environment variable for us to use later. So mine is 10.0.2.15. Yours is almost certainly not the same. So make sure that you use the one that actually comes from this hostname I command.
It's the first one.
Usually, yeah, the first one will work. Also, if you have Notepad or something or whatever, just like, it's probably a good idea to write it down because we're going to need to be copying it in a text editor later. So yeah, if you have a virtual machine, you might not be able to copy everything at once. But I'll wait a little bit. And yeah, make sure that you're not using the one that's up here for the IP. And then, yeah, so I'll go into step 5. So skip step 4 if you're done. Step 5, we're going to host the config files. So we just have to just run these commands in succession. We're just copying the config file into mlconfigfile.json on the web server. Then we just need to double check that the chmod that it's able to read write, because I have issues with that. And then you can restart the web server just in case. Shouldn't have to, but just in case.
You said skip step 4.
Yes. Just copy the commands for step 5. And then if you've done step 5 correctly and you have the host IP, you should be able to just run curl like this and download or it'll just like print out the contents of mlconfigfile.json. So when I run that command, I can see it just showed up. That means I know for sure that it's on that web server and that it'll be accessible to the xApp onboard and the components in the RIC when we deploy the xApp. So I'll give it a second.
I might need a second.
You're okay.
It's saying that there's no file or directory, so I guess.
Oh, you might have to do step 4. time. Already good on time, so it's great.
That's weird. It's saying that the file exists. When I do it in
Did
step
you?
4.
Oh, and you ran? Did you run the chmod 7? This one, or like on step 5, or are you saying that you got an error like trying the first command in step 5?
I got an error running the first.
Oh.
Yeah.
Huh. See.
I'm not running this from the correct.
Oh yeah, make sure you're in the xApp MLE2 like folder, because it copies from init/config.json. So if you're in the init folder, you need to go back one, or you just remove the init.
Yeah. Yes. Okay, yeah, we're good.
Awesome.
Yeah, I was wrong. Right?
All right, anyone else? Are we good? Okay. So we're also following the same steps. We have to create this onboard.url file, which points the xApp onboarder to our config file that we uploaded. So we need to remember what IP address this is, because we have to copy this. We create an ML onboard URL. We have to copy this in, but we have to replace machine IP address with the IP that you saved in host IP. So I will. Oh, great question. You should be in this xApp MLE2 like folder for the remainders, the steps for the deployment. So yeah. So it was for right now. I have it in here because I already did it once, but
So when we open the ML onboard URL file,
yeah.
It's supposed to be empty, right?
Yes,
Okay.
we're creating a new one. So it'll look like this, and we're going to have to copy this command right here, or I mean this JSON. It's like a little mini JSON. And there's this, the in brackets, or like the greater than less than sign. We're removing those, and the machine IP address. So, and then we have to type in the IP that we have. So for my case, it was 10.0.2.15. For you, it'll be something else. Just make sure that you remove those braces, as well as the machine IP address. So it'll look something like this. Yeah. So okay. Does anyone need me to wait for a second?
And then so you said for the rest of the steps were in the same folder.
Yeah, until I, well, yeah, until I say otherwise.
Do you have the project name?
The name of, wait, sorry, can you say it again?
No.
Okay.
Does anyone need any help? Going once, going twice.
All right. Then. So assuming we have that, so step 7 is where we're actually going to onboard and deploy this xApp. So there's a few steps, and it should be similar to what we did before. first, we're going to get the IP address of the Kong proxy. And the Kong proxy essentially is just a service that we can access different RAN components through different URLs through the same IP address. So it's a proxy to all the other components in the RIC. So we're going to first copy this command. So it should run without any issues as long, yeah. You shouldn't, well, yeah, you wouldn't be able to see anything from this, but what will happen is the next command is going to take the ML onboard URL file that we created, and it's going to submit that as the content, or it's going to submit that through a post request to this onboard download endpoint. So it will download the config file from that URL. So I will run that. I don't know what it will say because I've already done it. Okay, it says created. So this is what you should see.
Are these port numbers random?
The 32880 or the
Yeah.
That port number should be the same every time. It should be identical for the Kong proxy no matter how many times you deploy it. So if you mean like why they choose 3280, yeah, I think it's just chosen arbitrarily. But you do need to, yeah, but you need to make sure that this is the value when you run the command. Yeah. So is there anyone who doesn't get created or yeah, okay. So then the next thing is that we have the chart up. So all we can do, or all we have to do now is just tell the app manager to deploy the specific app we have uploaded. So in this case, if I run it, they'll say it's RIC app ML, this one right here. I think it'll give me an error because I've already deployed it. But if you run it, it should just work. For me, it gave me no response, which means that nothing happened because I'm pretty sure I already have it. For you guys, it should say like success. It returns some JSON, and inside it should say success. Yeah, wait, yeah. If that works, oh, well, actually, it's even here. It says, it should say this instance is null name app ML status deployed. So is there anyone who didn't get that?
There's a message there to decode JSON object.
Oh, so that means was that for, wait, so was it, which step? Are you running the first post step to upload the onboard URL?
No, the second one.
The second one caused it. Oh, make sure that, make sure that the spelling of this is, all of this is correct. Did you just copy the command straight in? Or, because the error is that it couldn't read this part of the command. Yeah, make sure that there is a single quote. Oh, also mine's cut off because it says, yeah.
Okay.
So if it all goes well, you should be able to check using this kubectl get pods A. And what you'll see is that at the bottom there should be a xApp RIC app ML that is running with all your other services. So Let's see. Once it's deployed, yeah. So just talking about behavior of how xApps work, or when we deploy things in Kubernetes, it's configured to automatically restart itself on failure. It'll continue to run even on a restart of the computer as long as the Kubernetes cluster is running. You'll have to manually restart an xApp through a command when you make changes, and you'll have to manually undeploy an xApp when you don't want it to be on the RIC anymore. So it doesn't just run once and finish. It acts as something that tries to continuously run. If there's an error with your code, though, it'll try maybe like 10 times to restart, and then it'll crash. So then you'll need to probably restart it. So is there anyone who couldn't get that to show up? Or are we good? Okay. So yeah, we have some commands here. These are just like a cheat sheet. We're going to be using some of these commands, but yeah, to view all the pods, to view all the services, to build a Docker image in our case, that was a xApp ML. How do we restart the xApp? We can view the logs using this command, and I'll just showcase that real quick. If I use the name that I get from the pods, this xApp ML, and we get this long string of hex number, or not hex, but just a bunch of numbers and letters.
Without adding that and show you everything in that particular namespace.
You mean like if I just put this in?
Or no, well, yeah, if you just do, well, I guess because there's the ML, that's different from the ICP side.
Yeah. It doesn't find all of the, it's not like a wildcard or anything. You have to type it in as is. Or there's also like an app equals, like, I think you can also do something like this. It's not, like, if you know the name of the deployment, I think you can use that as well. But yeah, you can just use the pod, and then, but you do have to specify the namespace. Yes.
I got you.
Please, I would like to interrupt for 30 seconds. So it seems that we have to sign on each day. Okay, so I will clear this sign sheet here. So during the break, please sign. Thank you. Remember, no signature, no lunch.
So I'm gonna restart mine just to show you, because we'll probably have to restart it as well if you're following along. Sometimes there's some stability issues, so I wanted to show it so that you can see what the logs look like right off the bat. You'll see that when you restart it, it'll like take some time to close the previous pod, and then you'll see a new pod spawn up. And you can see the age of the pod here, like 16 hours ago. This is 5 seconds ago. So if I run this again, we can see it's still running. So usually before using any, like, having the node be connected to xApp, I just give it a minute or so for the previous xApp to close. And we can see now there's only one xApp ML.
Is there supposed to be a RIC xApp?
The IC, no, that is just, yeah, it's on my system. So, because I'll show another demo later with a different xApp. So yeah, you should see, if we look at the logs, it'll just show something like this. E2 like enabled connecting using HTTP, and then we start the server. So we're ready to receive connections from the RAN in this case. So this is where we need multiple terminals open, or you need to use tmux or something similar for the next steps. It's going to be like, in day one, you might have had to do something similar, but we're going to need to start up all the LT components. So having the core, we're going to have a base station and a user running. And we're also going to be sending traffic over the network so that we can analyze what's going on with the xApp. So the xApp is already deployed, but let's see. We're going to need to do one extra step before we deploy before we start running SRS-RAN though. And that is that we need to expose one of the ports on this xApp so we can connect through the interface. So we need to run this command here. It'll give me an error because I've already run it, but what this does is essentially we use port 5000 in our Python script to accept messages, but we need to expose the port outside. By default, the pods and the Docker containers, everything in the Kubernetes cluster can't communicate with outside of that cluster. So, or at least no program can try to talk to one of the ports within the Kubernetes cluster, because it's all internal and virtual. So what we have to do is we have to find the port for our application that we want to connect outside of the network. And we create what's called a node port, and this gives us a port that we can access this port 5000 through. So basically we run this command. Should not give you this error, but
Does it have to be running the xApp?
it does not matter. I think, yeah, for a while, I think the next steps doesn't matter yet, but yeah. But I'm gonna be more specific in a second. But yeah, when you run this command, you can now run sudo kubectl get service A. I apologize for being confusing before, but Kubernetes services actually have a slightly different meaning. So when we talk about usually we talk about Docker containers and the pods and everything functioning as microservices. So the Docker containers contain programs that make up like one, let's say, service. But when we're talking about Kubernetes services, we're actually talking about the network connections between whatever application or program is in the pods, for example. So in Kubernetes, services are actually like we have IP addresses that are and ports that are associated with the different pods. In our case, we're looking for we created a service node port for xApp.ml, and we'll see that we have port 5000 is the one that we were exposing, but outside of the cluster, we have to use port 32199 to see it. So we're going to keep that port. Either we need to write it down, or we're going to save it for a second because we're going to copy it in later. So you mean like what's here, for example? So the cluster IPs are internal IP addresses. Well, actually, no, all of them are internal IPs within the cluster. Yeah. So you would be able to communicate. If you had something else in the Kubernetes cluster, you could use that IP to reach it. So, but for the node ports, we can actually use the main IP address that we collected here, and we can use this port 3433 or whatever, 32199 in this case.
That's specific to you.
That's specific to me. Yes. Sorry. Yes, it will be different for everyone. So we use that. This port we can actually access on our main IP address now using the port. And then that way we can have the RAN connect directly to that IP. So the steps are a little, I'm going to be cautious with following what's going on with the rest, because we need to create multiple terminals, where one is the core, one is ready to start the core, one is ready to start the base station, and one's ready to start the UE. So at least at first we need those 3 windows, and then we're going to spawn 2 more windows. So there's going to be 5 terminals that need to operate at the same time, at least. And then we're going to need a 6th one as well. So I would say, besides the current window for the xApp, because we're going to view the logs here, from what we were already doing before. So we'll view the logs here, and then we're going to create another terminal for the LTE core. And then we're going to create a window for the base station. And the folders where I am are not relevant right now. I'm going to show you where to be. And then we need to start a UE up as well. So, and then finally we need 2 windows to create iPerf. So I'm going to set those up on my system like that. Should have 6 windows total. I have an extra Python 3 window. You can ignore that. But so once you have 6 windows, then I would go to the xApp one. You can leave that alone for now because we've already deployed it. We need a window for the core. So we're going to follow step 4 here, where it says, assuming you already built the E2-like version of SRSRAN, you can go to the directory where SRSRAN is built. So that should be in your OAIC folder.
That should be on step.
Yes. It should, for step 4, it should be in the new terminal, or yeah, every terminal that you make can be in this new directory. Yeah. Because we need to be here for at least the core, the base station, the UE, we have to go to this folder. So OAIC SRSRAN E2 build, because that's where we provide our SRSRAN. So, oh no. And yeah, I'll wait a bit to make sure that you have you have 6 terminals here, probably in this folder. So, and then I'll start with the first step here, which is the EPC. So we need to start an LTE core. If you've done it before, you just have to run this command here, and it will tell me that the EPC is initialized. So, and the core can be running in the background while we're doing the other steps. So for the next step, I am not in the right folder right now, but let's see. And just let me do something quickly. So I'm going to make my setup look like yours, since I just want to copy the commands before I remove things. Okay, so we go to OAIC SRSRAN E2 build, and we're going to start up the base station in a second. But before we do that, we need to know the xApp port, and we need to know the IP, the host IP. So if you didn't, if you need to remake that environment variable for the host IP.
And quickly, at least for me, as I'm following along, since I'm opening a new terminal, I need to reset, re-CD to the correct directory, reset all these variables. So there's like a step where you go CD, what is it? OAIC SRSRAN E2 build, you need to CD to that directory and set your host name and set your xApp
Port,
before
yeah.
you do any of these. So you need to repeat that step multiple times for every terminal you move.
So, well, yeah. The one thing I'll say is that for the base station is the only one where you need the host IP and the xApp port.
Okay.
So
just that one.
you need to CD to everywhere else you need to CD. Yeah. Or I would recommend it.
That's one of the challenges I'm having.
Yeah.
And you need to reset the host IP for each.
or for at least for the base station, before you start the base station up, set the host IP. Yeah, so for the other ones, we won't need to use them. And then also the xApp port is the one that we collected before. So I will reiterate to collect the xApp, the xApp port. You have to do sudo oopctl get service A, and we look for the one that corresponds with RigApp ML. So I have 32199. You will have a different one, almost certainly. And then we go to our base station window, and we save the port as xApp port. So check with time. I'm gonna set this up. So
This is step 3 that you're on.
So step 3 is the xApp port step. It's should have, I apologize, because it could have been in step 3 and 6 are the ones that you have to do. Yeah. Because unless all your environment variables are saving between the terminals, which they only would if you ran these beforehand. Well, it's conditional, yeah. So like if you were running tmux, you have to repeat these steps unless you started tmux after step 3 and 6. So because it'll clone the terminal, but it'll only clone the terminal from when you started tmux. So yeah, I already had it running long ago, so and I'm sure most people did. So for the base station, I have the command copied in step 7, which is to start the base station. I'm not going to run it yet because I also want to start the UE up like as quickly as I can. So step 8. Yeah, you're good. I was thinking. So in the UE, so we have the base station window, but in the UE window, I'm going to run step 8, which is make sure that the UE1 network namespace exists. So I run this command in the UE window, which should be the 4th window that you have. And it should, I mean, if it gives you this error, that's fine because it already exists. Otherwise, it shouldn't give you anything, and that means that it works. So, so I'm going to load up that UE command. I'm not going to run it yet, just because I want the base station and UE to start around the same time. Then there's also like step 10, step 11. So we're going to want to also run these. Step 10 is running in another window, and step 11 is running in another window. So you'll have the core, the base station, the UE, then iperf3 server, which is a way that we're going to send traffic there, and then we have iperf3 client in 11. So when it's queued up, you'll see that I have all these windows. I have this iperf3 window here with this command ready to run. I have this IAP netns exec. This is the client side. Once the UE is connected, this command will start sending data from the UE to the base station. So I have all these commands queued up just so that's easier. You can also just run these commands as you go, but if you wait more than a minute between the commands, the UE will disconnect. So, or does anyone want me to wait first before I run this? Okay. Then I'm just going to demonstrate. For the base station, I might find that the xApp will crash, and in that case, I'll have to restart the xApp. And then in that case, I will restart the xApp and the base station, but I won't start the UE and everything until I know that the base station ran. So I'm gonna run the base station right now. Let's see if it connected. So we actually see that it established a connection, but we're actually supposed to continuously be receiving messages. If I see this, it means that the xApp didn't finish, or that it didn't establish the connection all the way. So I'm going to stop it, and I'm going to go back to this window that I'm using for the xApp. And I need to run a command here, this restart xApp command. So I'm going to let it restart for a second and make sure that the base station is good. I'll wait for this to terminate. At the same time, I'll also see if I can get the logs open, which is a command, it's this command here. Okay. And before I leave, we want to make sure it is closed. So I'm going to run the base station now and see if it connects. So now we see send IQ buffer continuously like this. This is good. We're seeing that we're actually sending data and we're receiving E2-like messages back. So you're receiving message M and Z. M represents changing the MCS dynamically, and Z represents a fixed MCS. So that's the commands that we'll end up seeing. If I look at the logs of this xApp, we can see that I'm constantly receiving IQ data. I receive a buffer, it says processing, and then I send the request back. When we make a decision, we decide to make a decision, it'll say interference signal detected, sending control message to enable the adaptive MCS, and then there will be a message to disable the adaptive MCS setting. So that's the base station, the xApp communicating. So we're good to now start the UE and establish some connections. So I'm going to connect the UE, and I can see that I attached the IP successfully. I'm going to then also start the iPerf windows and run these commands. So I don't see if any traffic's going through yet. Make sure that the base station crashed, that would do it. So I'm gonna run this one more time. So the base station runs first, then the UE, and then once the base station and the UE are connected, then we can run the iPerf command. So I can see that, okay, the xApp is talk to the base station fine, start to the user. I typed T in when I started the UE, and we see this trace pop up. Now I'm going to start iPerf and the other command. And now we actually see that there's some bit rate going on. So, so we can see that we are actually getting a connection, and we're sending data across from the user to the base station. And this reflects what's shown on the site as well. If you want to see that asynchronously, each command's output is also on the documentation. So I'm going to go back to the user, or so this is the user's trace. So when I typed T and I pressed enter, it gave me this. This statistic showcase, like table of there's MCS values here, and this is actually the value we're changing is the uplink MCS. So you can see that 28 is the fixed value that we started off with. And when we have 28, we have an error rate of about 35%. But when the xApp decides to change the MCS, then we see that the dynamic MCS is enabled and it goes to about 23, and then our error rate's gone because we chose a better MCS for our channel condition. We can also see this on if we look at the base station side, we can see that we're receiving the M and the Z messages. And if I take a look closer, okay, but yeah, the idea is that we're constantly receiving and sending requests, and then we're getting the messages back, which either send a Z or an M for enabling the MCS, adaptive MCS or non-adaptive. So if I look, yeah, sorry, if I pause for a sec again, I scroll up. We have inside of the Mac layer code, we have this E2-like command received that says using fixed MCS when we get the Z. But when we get an M instead, then it'll swap over, it'll say using dynamic MCS or adaptive. So that's what the base station is showing that. And then we can see the user where it's literally reflected on the uplink MCS. Every time it changes, every 8 seconds is what we set it to be. Then we see that we have an improvement in the error rate because of the control from the xApp. So in this way, like we're able to show that, you know, through this connection, through the xApp, or basically through the decisions that we're collecting information from the base station and using the xApp to make some informed decision based on, in this case, the IQ data, but it could be any other type of data. We're identifying like how this way that we can dynamically control the RAM through the rig. So you have or does anyone have any questions for this part? Yeah, there's a lot, so I do not blame you. It's just, I think, and I don't think you're the only one either, right? I'm pretty sure. Has anyone gotten like all of this to show up?
I mean, my issue is my VMs keep crashing.
Oh, okay. Yeah.
That's really about it. But.
Yeah. If you can get all the components running, good job. But yeah, it is. There's a lot of different moving components here, so if you just want to be able to see it here, that's also fine.
So I did try to run the Geno V. So I got the EPC launch.
Yeah.
I got an error. I think.
Oh, the EPC or the Geno V?
Well, the EPC is fine. Everything's initiated. But it's just the Geno V.
Sure. Check it quickly.
Actually, it's not really an error.
It just didn't show.
I'm telling you, man, like this thing it's not working for me right now.
Oh, wow. Okay. Yeah. Won't even start up.
Yeah, I feel like I don't know. Maybe the laptop doesn't have a leg.
I don't know. You're just using a VM on the system.
Yeah, so the Google, like the Google.
Oh, you're using Google Cloud then. Yeah. So it's like, well, it shouldn't be your laptop then. It's just.
Yeah.
But even then, like, I was able to get it to everything to pop up on Google Cloud. I'm not using it right now, but I did in the past. So.
Oh, I got this. So it's the argument option for rig agent. You should follow me. Yeah.
Oh, you got this.
Oh, I did it before I team up.
Oh, yeah. No, I guess you have to do it again. Yeah, sorry. Yeah, in terms of time, I'm actually ahead, so I'll give it a second for you guys to figure out if there's any issues. I might go around to help, actually.
Yeah, so I tried to set it. Try to.
Oh, xApp board also. Oh yeah, you can either run the git service command.
do this as quick as possible before it crashes again, but, okay. Yeah. Oh, there. Oh, but, okay. and then, so yeah. I have to kill my,
You have to kill the, yeah, I have to restart the xApp if it doesn't enter an endless loop like this. So, okay, does anyone need help right now? Yeah. Yeah. Oh. Did you have the, like, so this is from yesterday, like, yeah. So you might need to kill the previous, like if you had the core running, you might have to kill it. So you can do sudo pkill. Pkill space dash 5. And then space src. Yeah. And then
Right,
yeah.
so I, if you see that, I probably, one of which is just sitting there and listening, the other is shoveling data.
Oh, okay. So
I heard that in using
Easy. After this,
It's just the VM, or the VM every time it crashes.
Oh, you also
easy because of the
computer? I don't think so, I think it's just the VM, like, I think it's like,
oh, Google, right?
yeah.
And you did that. Still it is, so even Google is not stable.
I guess not.
Yeah, they are supposed to be powerful.
I thought so, I mean, I don't, I guess, unless everybody else having the same problem.
I thought Google, or you'll be the level. You don't know.
Actually, my thing started working quickly when I
When you switch.
Oh, really?
Yeah, I don't know. It might have to be actually,
you have to run the
so
right
just every
after.
time I try to type something, well, I mean, it's fine now, but it'll randomly just stop.
Yeah, so you have to run the second time.
but like it's very not frequent, smooth working, like
Yeah.
that yesterday it happened because of the connectivity.
So
But
are you?
otherwise, I think I have faced it only once.
And then once you
What demonstration? So I did. Me too.
Oh, you are also.
Yeah. That's weird. I mean, other than that, I'm following along fine.
Do you have any other
I got like, I mean, this probably is an issue. I got a lot of windows.
yeah, because my laptop took me one.
start the you. Run the yeah, then run the run that. And then open up a new terminal. Go back to the
Wait,
I think it should be. Oh, okay. It was one. I don't know why. Oh, so it's the IP of the host, not the IP of the user. Yeah.
That's.
Oh.
Because you see, it is.
Wait, that was a mistake. Yeah, thank you. Sorry about that. I think the whole sentence is weird because it is the other way.
Yeah.
That whole sentence is it's actually the PI which is it should be point two. Yeah, so you're actually so if you go to the oh, it crashed. Yeah, so it just crashed.
But it's just.
So it was working. Yeah, it was working. I think the base station. So the only problem with the IQ data that we're taking is like the KPM data is just that too much. No. It isn't direct. Wait, you mean like oh yeah, so oh and yeah, but what we did, what should have happened, we exposed the SCTV storage like in the so instead we actually created a report for the xApp and that it just exposed it and we didn't recommend it. So if I pass all the models and everything, so even if you're going to put the if this is the problem, if it is not what it is established, so it's not so it's like yeah, so it didn't
So you automatically use the which is the
so I think okay. So it can find the run yeah. Yeah. So it's like, oh yeah, you can do yeah. So this, then, or sorry, that was actually. Then run yeah, so even the connected with the, oh, so that oh, I know the problem. Sorry. I made it. Okay, the problem is that I made the change 3 years ago. It's not just, it's you can add the SCT yeah, so I think I'm running this on yeah. So I made a mistake here. It's actually there's changes to the point. No. Well, but I can't. I was about to. I can't. Yeah, no, it's actually like it's a basic. I need to follow it. Yeah, it's documentation. Oh, I use. Yeah. I think just trying to connect with myself. I'm trying to connect with yeah, almost. Maybe. Oh, if it was. Oh, you have to. You mean you have to. You have to. Yeah. 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 Or no, don't you make sure you're not. So if they're already like that. Yeah, I think or the connection like it like synchronized me. So to fix it, you have to this is yeah, you can restart the pod. So it's also if you you want that. You can also do I just every time. Yeah, no problem. And then also when you restart the xApp, you need to close the base station and then restart it and then start the base station. Can you show me the base station? Oh, okay, the xApp, or like so you have to restart the xApp, or we have to close the base station and then you have to restart. So you can you don't have to close it.
No, you have.
Yes, you can close that and then close the close that. Then you don't have to keep that. So you have to run the command in the document. What it's called. It's higher. It's called rollout or just every technical. So the reason is that sometimes the request, like we send the initial request to receive data, right, and it's not picking it up.
Looks like this, I can still see Zoom. See, so we are good, we are recording.
So yeah, that might set up like request, right? Sorry, the rant's supposed to send back. But like if it didn't catch that, it'll just try to go. It'll just hey, like it won't the xApp will be so you're so yeah, it didn't change because the xApp didn't change it. It was the xApp wasn't functioning, but the base station user were talking. Give it like, or you can also check the pods. Does it get pods? Pods or feeds? Or get pods. So okay, it's good. So yeah, you can run the base station. Yeah, that's right now. Start the hyper. Yeah, the other one. Sorry, the pseudo IP. Now go back to my heart's not just letting it go. It's like it feels like I'm running. Okay, so when the time should change. Okay. So I was having this was you're using AWS. Yeah, it's like you basically have it working right now. Just set the xApp to turn on the SR side. It isn't the command isn't requested in the Mac. So yeah, you did run it. It's just now there might be like the MCS changing, but everything is otherwise. Yeah, probably.
terms of time or I think most people got it, or well, people seem to be getting it to run. It's just the only thing is, I think for some people the MCS isn't changing over, but the xApp and everything else, everyone's been able to get, or I've been getting people to have the whole loop running with xApp and the base station. So, yes, yeah, I showed them, and I'm going to finish off with the demo. 20. Yeah, I timed it to 11:45.
Okay, last call, does anyone need help for this?
Yeah, I think we're, yeah.
Hey, looks like we are very high. Anyone else? Oh, you are helping? Oh, you.
I'm trying to go. I'm trying to trying to do this as quickly as I can before it crashes again. Oh. Oh, I crashed. Yeah.
So I asked Anya to stay there on lunch, so we can stay there.
Beating out my chest. Yeah, running all day. There might, I don't know if there might be a thing already, but I just kind of give it to her or something. Sure. We got a warning. When we were parked, they didn't charge us anything, but they were. We didn't warn you, you just parked out of there.
I don't know, I will see, maybe I will get one, maybe they are going around and finding.
I have no idea, I need to go check because, yeah, I don't. Yeah, well, so that's what he said, he said that they went out and they showed where to park, but they're.
And you guys are using what same car, I mean.
Yeah, we get together.
I will see what.
Yeah, okay. I mean, I don't want to get taken. Yeah, it's for the. Right. Okay.
So as long as it is not some characteristic or service or handicap, then you are.
Yeah, it was just a regular.
Regular spot.
There was no soccer.
Yes, if you come from Black do you come from Black?
We went,
Or the other side?
we went all the way around again.
In general, you come on Black.
Yeah. Yeah.
So I entered yesterday, just with the gate, there is a turn, you can make it the back.
Yeah.
So he went inside and then out.
Right.
There are so many spots, there is no any sign that mentions specific things. Nothing. It just says there is in front of the other building.
Yeah, but you can, it's front facing this.
Yeah.
Sounds like you're fine.
At least yesterday they didn't do anything. Oh, you parked again the same spot? Oh.
We thought that's what we're supposed to park.
But when did you get the warning yesterday?
Yeah.
There is a parking spot, you need to register. Have you registered your car?
I let her know.
Oh, no, there is some registration.
Yeah.
So there is a registration link and there is a code.
Yeah, we didn't.
Yeah, I think when you do provide a license plate, that's what I do.
Yeah. I saw that email.
You confirm, send the email. And tell her that you got this, is there any code and the registration link where I should register?
Okay.
All right. I'm gonna show a demo in a second. The master has been built. So you. Like that. The error itself is saying that it can't. Okay.
Yeah, we do. We'll put it in the process.
I wonder if it's the network. Yeah. It says already. Yeah.
So what do you do?
I directed the yeah. I think, okay, what's this failed to send? So I think that this is the either the exact either that or the XS, or it's either the basic or the XS. Like it did, I don't think the XS crashed. But if the basic crashed. Yeah, but because the basic is running, so I think there's the I think it just failed to send twice, so I think it got like
You have your own base station. So what do you say?
So, yeah, so we have a software.
yeah, so right now, because it's all of the media, one that you like, and mainly we just want to separate those rules because of all like the interface, also have OAIC, radio, but it's just working more with third party radio now. We're doing the network,
Yeah, what is it?
yeah, the net, yeah, yeah.
There's two ways to do it.
Yeah, we're trying to get started. I wasn't supposed to have software, but we had trouble writing. So it's better to have it. Now I'm not.
Well, we had to write our There's a lot of
Okay, so quickly, so I'm going to show a demonstration that expands a little on what we were showing for this xApp. Essentially, I'm going to be running a KPM or an xApp that can identify interference through KPMs, and then change the MCS like we were seeing before. But yeah, instead of IQ data, we're using KPMs, and and we're also have like a visual display that we're using GNU Radio to visualize the type of system that we're going to be running. So I'm going to close everything. And I have an xApp that I'm just going to run locally for now, just to showcase this. I'm going to prepare these commands. And I'm going to give myself a visual. So I have a system set up for GNU Radio, and through the system, we're actually able to we're able to combine some of the signals, like not only just the base station and the UE connecting to each other, but also being able to introduce like factors of like noise, path loss, having some like radar, and also some interference. So I'm going to run this graph here. And I also will start up this system. So we already have the node B running. Let's make sure that we're using KPMs now, so we can see there's SNR, there's bitrate, block error rate, MCS, BSR. No users connected yet, so we don't see anything. But when I connect the user, I need to run a slightly different command. So the user's connected. I'm going to send some traffic over. And that's showing up. So while this is running, I'll see if I run the xApp. So we can see that there's a decision that the interference is detected or not detected. We're receiving 20 bytes at a time. So when we're receiving less data like this, the interface is more likely to be stable. But also, we're sending individual requests for either KPM data or IQ data. So if I take a look at our graph now, you can see that we're actually able to see like what the spectrogram for the 5G signal looks like over time in this waterfall display. And at the same time, I'm going to monitor the user, so we can see like how it affects the network. We're basically acting as a simulation here. So we have like 35% error rate. If I wanted to increase the error rate, then I could obviously just like turn up an interferer, so that's like 40%. And it might not be super visible, but if I make it really strong, it'll definitely be visible that there's a line right here where I'm just introducing a continuous wave interference. So it's just interference that is directly in the line of that's just like a certain frequency with a given strength. So I can change, just with GNU Radio, you can do things like being able to change, where the parameters of the different signals. I could make the user have a weaker signal as well. So you can use the xApps in combination with some system like this if you're using GNU Radio and 0MQ, or you could run this on on SDRs even, and you can evaluate like how the network performs and how your xApp performs when you introduce different factors. So right now I put too much interference that the user disconnected. But yeah, so you can see that I was able to introduce radar, which is just you just see a bunch of horizontal lines on everything. But yeah, so this is something that we're working on for the next G Wireless Lab, and also for an OAIC wanted to showcase. This is the type of work that this is the type of system environment that you can create with OAIC. And so, yeah, and further, this is why it's important to demonstrate this xApp development, why we're doing everything here. We can make decisions to dynamically control the RAN and how it behaves, improving the signals and performances. And we provide that test environment for you, or in the environment for you to be able to simulate and see what happens for whatever situation you're going through. So, is there any questions? Because this is the end of the presentation for this.
Are you viewing the MCS change in the constellation that constellation has there?
Oh, I didn't think about that, but yeah, so for this one, we have a KPM model that's present on here. I mean, it would affect the signal, but I might have to manually change it because it's a bit iffy when we found that let's say we're only working with 10 data points.
Yeah.
The KPM's accuracy is lower, and it has to be able to detect the point where that signal degrades instead of just seeing that the signal is degraded in general for the KPM model. So right now, the MCS is not changing super reliably. I could swap it to force the UE to have a different, let's say MCS. We actually left it in the argument here. So if I want to set to 8, and then initialize the connection one more time. Do it quickly just to show it. So it should be the case. Yeah, okay. So now the MCS is 8. So if I yeah, so I can't dynamically see the change because there's not that much but yeah, if I enabled the dynamic change all the time, which I could, then you'd probably be able to see through the constellation.
And then are you doing a dynamic channel block for the noise, or
So, well, essentially, I mean, for the interference, I mean, yeah, I could, I'm not doing anything to mitigate anything in any specific channel, but I can, specify if I want to put interference at a certain frequency, then I can move it from there to here or something. So I'd be affecting, the scheduling process and everything like that. And then when the signal's strong enough, then it'll just overpower everything, and then you won't be able to get any communication just because the SNR gets weaker. So sure. Yeah. But yeah, so this one is something we're going to demonstrate. But yeah, thank you. All right. Well, if there's no other questions, yeah.
One quick question. So basically, the scenario here is you have the G.B here, or in this case, we have the base station here, we have the UP here, and we have the radar.
Yeah.
And then the radar is always on?
So for this scenario, we're testing different interference environments. So we have both radar, and we also have just some interference that's happening in we have a wide radar that's affecting a large amount of frequencies, and then we also have a targeted single interference. It could be a radar, it could be some other form of interference, which is what the CWI is. So in this case, we're showing that you could have some xApp in the environment be able to react to those changes and we can do that through SRS-RAN and we use GNU Radio as like the ends to be able to combine those signals and everything. Because SRS-RAN, we use 0MQ, and using the 0MQ messaging system, we're basically just able to manipulate all the samples virtually. And we can combine using GNU Radio. We could also receive both like virtual and real radio signals. So if we had hardware, we could also use those as well. So.
And the path loss, could you basically vary how far it is?
Yes. Yeah. Yes. So, and even with the significant path loss change, we have the gain pretty high in the virtual signal. So it's able to sustain. But yeah, that's what we're just showing, like different parameters that you'd be able to manipulate.
Are you running UDP or TCP? Are you doing Hyper?
Yes, that's a good question. I think we're doing TCP, unless iFirst default is UDP. I thought iFirst default is TCP.
Shouldn't interference kill the link? Or it's very deep.
Oh, yeah. So if the interference is strong enough, it'll just kill the link for a pretty long. Yeah, it'll just like, so if I put the radar up to like 39, you'll just see that it just dies out. You also see that physically the signal on the spectrogram, if I put high enough, it'll just drop out. It'll completely disconnect as a result.
Which means that it has to come back again through the registration and all that.
Yes.
Yeah, like at that point it has to re-register, find the cell again, and do another connection through that empty point here. So, yeah.
Normally, when we say registration, it has a specific meaning in file. Okay, meaning the device uses connectivity even with the core network. Normally, that should not happen. Okay, normally the radio network should go away. Okay, if the radio network goes away, meaning the connection goes away, it means call would drop. So the data radio barrel goes away. But it will look for that cell or another cell. Okay, then after a few seconds, then it will really use the radio connection. So first you lose connectivity for some time. There is some time or like a radio link control that will expect. Then it still cannot find this cell, then it will look for other cell if you enter the idle mode. So there are all these things, but you still have the IP address. I'm not sure about this specific setup, but in a typical 5G network, the device will enter the idle mode, but it still has the connectivity. It's still a registration is still there.
But in this case, if the radar is there for a long time, it's gonna do it.
Yeah, then it will enter the idle mode and look for another cell. If this cell doesn't work. And it can run different kind of frequencies. In a practical.
Yeah, thank you.
So you are done from your side?
Yeah.
Do we have any questions for Nathan? Okay, thank you very much.
Yeah, thank you all. Thank you for being patient.